Hello everyone, and welcome back to another daily LeetCode challenge. Today's problem is LeetCode 3652, best time to buy and sell stock using strategy. You're given two integer arrays of the same length. The first array, prices, represents the stock price on each day. The second array, strategy, represents the trading action taken on each corresponding day. Each value in the strategy array has a specific meaning. -1 means buying 1 unit of the stock, 0 means holding the stock, and 1 means selling 1 unit of the stock. You're also given an even integer k. You are allowed to perform at most one modification to the strategy array. This modification works as follows. You select exactly k consecutive days, set the first half of those days to 0, meaning hold, and set the second half to 1, meaning sell. The profit is calculated as the sum of strategy I multiplied by prices I for all days. There are no constraints on budget or stock ownership. Your task is to return the maximum possible profit you can achieve after applying at most one valid modification. This means you can buy or sell freely, regardless of what happened on previous days. Your task is to return the maximum possible profit you can achieve after applying at most one valid modification. This problem combines prefix sums, sliding window techniques, and optimization. Let's walk through an example next to see how this works in practice. Example 1. Let's walk through the example to understand how the modification works. The input is prices equals array of 4, 2, 8. Strategy equals array of -1, 0, 1. K equals 2. First, let's calculate the profit using the original strategy. We multiply each strategy value with the corresponding price. That gives us -1 times 4 equals -4, 0 times 2 equals 0, 1 times 8 equals 8. So the total profit is 4. Now, since k is 2, we are allowed to modify any 2 consecutive days. For each modification, the first k divided by 2, which is one element, becomes 0, and the second k divided by 2 becomes 1. Let's modify the subarray from index 0 to index 1. The strategy becomes 0, 1, 1. Now we calculate the profit again. 0 times 4 is 0. 1 times 2 is 2. 1 times 8 is 8. The total profit becomes 10. Next, let's try modifying the subarray from index 1 to index 2. The strategy remains -1, 0, 1, which gives the same profit of 4. Among all possibilities, the maximum profit is 10, and this maximum is achieved by modifying the subarray 0, 1. That's why the final answer is 10. Example 2. Now let's look at the second example. The inputs are prices equals array of 5, 4, 3, strategy equals array of 1, 1, 0, and k equals 2. First, we calculate the profit using the original strategy. We multiply each day's action by the corresponding price. 1 times 5 gives 5, 1 times 4 gives 4, 0 times 3 gives 0. So the total profit is 9. Next, we try all possible modifications of length 2. If we modify the subarray from index 0 to index 1, the strategy becomes 0, 1, 0. The profit is now 0 plus 4 plus 0, which totals 4. If we modify the subarray from index 1 to index 2, the strategy becomes 1, 0, 1. If we modify the subarray from index 1 to index 2, the strategy becomes 1, 0, 1. The profit becomes 5 plus 0 plus 3, which totals 8. Both modified strategies produce less profit than the original. So the maximum possible profit is 9, and it is achieved without making any modification. That's why the final answer is 9. Now let's break down this optimized solution and see how it efficiently finds the maximum possible profit. Step 1. Pre-compute daily profit contributions. SP equals star P for SP in zip strategy prices. First, we combine the strategy and prices arrays. For each day, we multiply the trading action by the stock price. This gives us an array called SP, where each element represents the profit or loss for that specific day. Step 2. Basic setup. N equals len prices. Baseline equals sum SP. Here, we store the number of days in N. Then we calculate the baseline profit, which is the profit without applying any modification. This is our starting point. Step 3. Understand the modification window. H equals K times 2. Since K is even, the modification window is split into two halves. The first half becomes hold, which contributes 0 profit. The second half becomes sell, which contributes the stock price. Step 4. Initial window calculation. Old equals sum SP plus K. New equals sum prices H to K. Here, we calculate two values for the first window of size K. Old is the original profit, contributed by the strategy in this window. New is the profit after applying the modification. Notice that only the second half contributes profit, since selling adds the stock price. Step 5. Track the best improvement. Max diff equals max 0, new, old. We compute how much better the modified window is compared to the original. If the modification makes things worse, we simply ignore it. Step 6. Slide the window across the array. For R in range Kn, now we slide the window across the remaining days using a sliding window approach. Update original profit. Old equals SP minus SP lel. We add the new day entering the window and remove the day leaving it. Update modified profit. New equals prices R, new equals prices L minus 1 plus H. We update the modified profit efficiently. We add the price from the new sell day and remove the price that is no longer in the sell half. Update maximum gain max diff equals max diff new minus old. At each step, we update the best improvement we've seen so far. And final answer, we return baseline plus max diff. And that's how this solution efficiently maximizes the profit. Now let's run the code and confirm that it passes all test cases. All right, everything looks good. Let's go ahead and hit submit. And there we go, accepted. All test cases passed successfully. This confirms that the sliding window optimization works exactly as intended. If you found this explanation helpful, don't forget to like the video, subscribe to the channel, and share it with anyone preparing for coding interviews. I'll see you in the next daily LeetCode challenge. Until then, happy coding.